Alright, so for this first video we're going to be looking at lessons 1.2 and 1.3. Again, this is just a precursor to the lecture that we'll do in class. So finding limits graphically and numerically. And so just as a quick heads up, by the end of this video you should be able to find a limit using the numerical approach, the graphical approach, and the analytical approach. And you should try to do it in that order. You'll find that numerical and graphical may sometimes take more time, but they develop a better understanding of what a limit is. So you're probably asking yourself, what is a limit? And my answer to you would be, once we get through this example, you'll get a better understanding of what a limit exactly is. For this first example, we're looking at the function, a rational function, which is x cubed minus 1 over x minus 1. And we're going to look at this limit of it because that's what we want graphically. So what we're looking for here in this example specifically is limit as x approaches 1 of f of x. So that would just be the limit as x approaches 1 of x cubed minus 1 over x minus 1. Now you're probably wondering, well, why did I pick 1? And part of the reason is because when we plug in 1 into this function, we end up getting an issue, right? We end up, if we plugged in 1, if you look down here at the bottom in this chart, we get a question mark. And the reason why it's a question mark and not undefined or 0 is because it gives us what's called an indeterminate form. X, when we plug in 1, so we can just do that right now, we get 1 minus 1 over 1 minus 1. Which is 0 over 0. This is an indeterminate form, okay? It doesn't mean 0, it doesn't mean undefined, it just means we don't know yet exactly what it is. So when we're looking numerically, if we plug in 1, that's not going to help us figure out what the limit is. So instead, we're going to take numbers that get closer and closer and closer to the value of 1. So if you look at this chart, we've got 0.75, 0.9, 0.99, 0.999, 1, 1.001, 1.01, 1.1, and 1.25. So if you notice, I guess you might have started to pick 1.25 and 0.75 are actually really far from 1. The closest we got was 0.999 and 0.001 after the 1. And so what we did is we plugged all of those numbers in to our original function, which, as a reminder, is x cubed minus 1 over x minus 1. So when we plug each of those in, we get 2.313, 2.710, 2.970, 2.997. So as we get closer to 1, as we're increasing towards 1, our function f is approaching 3, right? Because 2.997, if we were rounding that up from 2.9, that would be 3, right? So we're approaching 3 from that side. As x decreases towards 1, f of x, if we notice, also goes towards 3. Because our values are going from largest to smallest for x. They are 3.813, 3.310, 3.030, 3.003. Okay, both of those, both 2.997 and 3.003 are really close to 3. So by looking at all of that, what we can then say, based off of that chart, limit as x approaches 1 of x cubed minus 1 over x minus 1 is equal to 3. Okay, that is our limit. Let's now look at it graphically. Okay, this is the graph of the function right here, this red line, this red curve. Okay, and what we're going to do is, I like to imagine like the function curve is like a road. Okay, a road has two sides. You've got people coming from the left and people coming from the right if you're standing in the middle, right? So let's say we want to get to 1. So then 1 is our middle point. So this is where you would stand if you were in the middle of the road, right? And you've got cars coming from the right and cars coming from the left. And for a limit to exist, the cars have to crash. So we ask ourselves, if we were to act as two cars and we're coming towards one, do the cars crash? And the answer is yes. And specifically, they crash at the y value 3. So our limit as x approaches 1 of x cubed minus 1 over x minus 1 is also equal to 3. So numerically and graphically, they both tell us that it's 3. So we can then say that it definitely is 3. So from all of this, what we then develop is the definition of limits. So saying that let c be a real number, then the limit as x approaches c of a function f of x is equal to capital L. Okay, so 3 is our capital L in this instance, and our c was 1. More examples. So let's look at the example on the left side of the screen. We've got limit as x approaches 0 of x divided plus 9 minus 3. And we're going to look at this one numerically. Okay, so I created a table. And so we notice that we're approaching 0. Okay, and so 0 is here. Now you're wondering why the value on the other side is blank for 0. And that's because if we plug in 0 into our function here, we get 0 square root 0 plus 9 minus 3. This is 0 over 3 minus 3. This is 0 over 0. So when we plug in 0, our function is an indeterminate form. So that's not really going to help us very much, is it? Instead, we take numbers that are getting closer and closer to 0. So I've chosen negative 0.003, negative 0.002, negative 0.001, 0.001, 0.002, and 0.003. When we plug all of those in, if we're coming from all the numbers that increase up to 0, so that's the negative side, we are getting closer to 6, right? Because 5.9998 is pretty close to 6. And as we go towards 0, where we're decreasing it, so we go from the positive side, we also get towards 6. So then we can say our limit is 6. For the next one, we've got a piecewise function. Okay, right here. So that's when we have something broken up out across an interval or across a set of values. So here we've got that f of x is equal to 1 when x is not equal to 5. So that's every other number except for 5. And f of x is equal to negative 2 when x is 5. Okay, and so we're going to look at this graphically because I think that's going to be easier to understand. So when we look at this graphically, this is the value f of x equals 1, and this is the number negative 2. Okay, so if you notice, there's a big difference. When f of x is equal to 1, it's a long line with only a break right in the middle here at 5. Whereas for negative 2, it's just a point, and that's because f of x is only negative 2 at the value 5. It's not negative 2 anywhere else. That's why it's just one point here. Okay, so when we're looking at the limit, we're going to again use that car analogy, okay, because this tends to throw people off. We need to know if it's going to crash. We've got a road here on 1. All right, so as the limit approaches from the left side, so this is all numbers less than 5, we get close, and when we approach from the right side to 5, we also get close. Now this little dot in the middle, imagine it like a pothole. You have to think about it. If you ever drive over a pothole, does your car just stop when it reaches a pothole? Does it just drive through the pothole? It drives through, right? So our cars will still crash even though there's a hole in the middle. So our limit, because the cars crash, is going to be 1, not -2. In fact, -2 doesn't really factor into this at all. At graphic representations of this. So next we've got the limit as x approaches 0 of x over the absolute value of x. So first thing we're going to talk about is tells us absolute value of x means that it's equal to a positive x whenever we're greater than 0, right? And it's equal to a negative x whenever we're less than 0, right? When we're actually looking at a limit of a function that involves an absolute value, we actually can break it up into a piecewise function. So we can have the limit as x approaches 0 of f of x, where f of x is equal to x over positive x when it's greater than or equal to 0, and x over negative x when it's less than 0. Which just simplifies to 1 when it's positive and -1 when it's negative. Now, staring at this, do you think this is going to have a limit? So let's go ahead and go to the graph version of this then, so we can kind of talk about it a little bit more. This is the graph of our function. We have two separate lines. We have one here above the x-axis, that's positive for all positive values of x. And then we've got one that's negative for all negative values of x. If we took two cars and we ran them along, so we've got one coming this way and one coming this way, do you ever think those cars are going to crash? If you say no, then you are correct. So, in fact, it turns out there is no limit of this function. This limit does not exist. Or DNE for short. Let's look at another example. We've got limit as x approaches 0 of 1 over x to the 4th. Again, we're going to do the graphic representation of this. So we've got our graph right here. Okay, this is 1 over x to the 4th. If you notice, the left-hand side of the graph, so that would be this curve here, goes all the way up forever, right? It gets huge. That number just goes up and up and up and up. And then as we approach from the right side, again, that number just gets bigger and bigger and bigger. So because the numbers get so big, we can say that this limit does not exist because those numbers are just going to keep going up higher and higher and higher. So the limit as x approaches 0 of 1 over x to the 4th does not exist as well. Move on to finding limits analytically. Okay, so before we go into any sort of examples, let's talk about some basic limits and some limit properties. And theorems 1.2. So to start off with 1.1, it says let b and c be real numbers and n be a positive integer. Then the limit as x approaches c of b, which is just a number, right, is b. So if we had limit as x approaches 0 of 1, it would be 1. Then we've got limit as x approaches c of x is equal to c. And then we've got the limit as x approaches c of x to the n is equal to c to the n. For the properties, we have, again, some conditions we have to talk about first. So we're going to let b and c be real numbers, let n be a positive integer, and let f and g be functions with the limits limit as x approaches c of f of x is equal to L, and limit as x approaches c of g of x equal to k. Okay, So the first one we've got is when you multiply your function by a number. So in the first one, we've got limit as x approaches c of b times f of x is just equal to b times your limit. And then for 2, we have the addition or subtraction of two functions within a limit. So limit as x approaches c of f of x plus or minus g of x is just equal to the limit of f of x, which is L, plus or minus the limit of g of x, which is k, over here. For 3, we've got the limit as x approaches c of f of x times g of x. That is equal to the limit of f of x, namely L, times the limit of g of x, which is k. For 4, we've got the limit as x approaches c of f of x divided by g of x. This is equal to L divided by k, where k does not equal 0. Okay, we can't have a 0 in the denominator, right? And lastly, limit as x approaches c of f of x to the power of n is equal to the limit of f of x, which is L, to the power of n. So all of these should come in handy as we go through this lesson. Examples. So first, let's look at the very top one here. Limit as x approaches 2 of x cubed. To find the limit as x approaches 2 of x cubed, we are going to substitute in 2 for x and just cube it, which is 8. That's pretty simple, right? Let's do another one like that. We have limit as x approaches 4 of 8x. Again, we're going to replace x with 4, drop the limit notation, and so our limit is 32. One more of those. We've got limit as x approaches 16 of the cube root, the fourth root of x. So again, first thing I'm going to do is going to drop that limit notation and write the fourth root of 16, which is equal to 2. Next, we're going to look at a polynomial. Okay, so we've got limit as x approaches 2 of x squared plus 5x plus 4. This is going to, what we're going to do is same things before. We're just going to replace. Every time we see an x, we're going to replace it with 2. So we drop the limit notation, get 2 to the squared plus 5 times 2 plus 4. This is 4 plus 10 plus 4. This is 18. We'll do that one more time. This time we're looking at a rational function, so that's a function divided by a function. Again, we're just going to plug in a 2 everywhere we see an x and drop the limit notation. So we get 2 squared plus 5 times 2 plus 4 over 2 plus 4. This is equal to 18 over 6, which is 3. Now we're going to look at limit as x approaches negative 4 of the cube root of 2x squared minus 5. So again, first thing I'm going to do is drop that limit notation and replace every time I see an x with a negative 4. So we get the cube root of 2 times negative 4 squared minus 5. This is going to be the cube root of 2 times 16 minus 5. This will be equal to the cube root of 32 minus 5. This will be the cube root of 27, which is 3. Now let's look at one where we have a trig function here. Okay, so there's a chart on page in your book that lists all of the limits, basic limits of your transcendental functions, that's trig functions, and logarithmic functions. So limit as x approaches 3 pi over 4 of tan x is, we're going to do the same thing we've been doing before. So we're just going to replace every time we see an x with 3 pi over 4 and take away the limit sign. So we have tangent of 3 pi over 4. From the unit circle, we know that 3 pi over 4 is a standard angle, so this will be equal to negative 1. And lastly, we're going to look at the exponential function e. So again, only thing we're going to do here is drop that limit notation, replace the x with 2, and simplify. So we get e to the 3 times 2, which is equal to e to the 6. And that would be it.